Assalamu alaikum. Welcome to another session of data structures and algorithms using C++. My name is Dr. Bilal Wajid, and today we're going to talk about functions. Now, functions really help us break down larger, more complex tasks into more manageable subtasks. Now, consider the following function. The function itself is, it seems pretty complicated. But we can in fact program such complicated functions using smaller sub-functions which somehow work seamlessly when working together. Now consider this. Suppose the same function that we are looking at is actually 4 sub-functions, where this is f1, this is f2, this is f3, and this is f4. If we look at the first function, it's actually 1 over Rn. Now it's 1 divided by Rn, and this particular Rn can actually be written as power Rn. In fact, there is a built-in function within C++ by the name of power, which the first comma next is actually a raised to the power b. In Rn will actually be r raised to the power n. So in fact the first function can be implemented with the inverse of the power function. So let's see how would you program something like this. Now here the function has been represented again for instant reference. We see, well, the function is 1 over power Rn, so that tells us, well, the function f1 requires 2 inputs, one is r, one is n, and that's what we see here. The return type is double because it is an inverse, so double function 1, integer r, integer n. And we see really it's a simple, because you could have written just return 1 over power Rn, or in this case we've written double answer has been assigned 1 divided by power Rn, and then return answer. If you notice here, power is written in blue color, and so is this C math library. In fact, it is the C math library of which this power is a function. So we do need to include the C math library in order to run the power function. So having managed the first function, let's go back and look at the function again. So this was the function that we are trying to make. I've colored f1 because we've already understood how we are going to make it, and we've already programmed it in the last slide. Let's consider now the second function. The second function is a binomial coefficient series, and this n choose k is actually equal to n factorial over n minus k factorial. As you've noticed, I've used the word factorial a lot. So the fundamental function here is that of factorial. And what is defined by a factorial? Factorial s can be written as g of s, where s factorial is actually s times s minus 1 times s minus 2 all the way till 1. Alternatively, you could say it is 1 times 2 times 3 times all the way up until you reach s. So the same function that you see here can be represented by these functions, calling out this function again and again and again, but giving different arguments. So the numerator, because it's n factorial, I will pass n as an argument to the function factorial. In the denominator, I have n minus k factorial, so I'm going to pass the function I'm going to pass n minus k as an argument to the function factorial, and I would do the same here. How would I program this? Well, let's have a look at this again. This is function 2, and I've mentioned what the gist of the function is from a programming standpoint for instant reference. The first thing is, because the function f2 is dependent on the function factorial, we need to write the function factorial first. So double factorial integer s, because it really requires just one input, as we've mentioned here. And all we are doing is, if you look at this for loop, it starts with 1 and it continues up until it reaches s. So it is really 1 times 2 times 3 all the way till it reaches s. And answer is really answer times I. So in the first loop it is 1, answer is 1, so 1 times 1 is 1. In the second loop I is 2, So 1 times 2 becomes 2. In the third loop, I becomes 3. So 2 times 3 becomes 6, and it grows accordingly. Now function f2, notice here there are two variables. We need n and we need k. N minus k you can figure out automatically. So there are two independent variables. One is n and the other is k. So the function f2 requires two inputs. One is integer n and the other integer k, as has been mentioned here. And really it's a very simple function because we've declared a variable answer, and answer is factorial n, which is this guy here at the numerator, divided by the product of factorial n minus k and k, as can be shown in the denominator. Now I've marked this as blue because the function factorial depends on the function 2 depends on the function factorial. Therefore we're actually calling out this blue function here 3 times. And because function 2 is dependent on factorial, you have to define factorial first. Now let's go back to our complicated function. Looking at it again, we see, well, we've already figured out how to program these two functions. Let's talk about the third function. The third function is written here. Again, we see this common factorial component, and this can be written as factorial m, and now we have a summation of, rather a series of sums of the function factorial m. So it starts with 1 and ends at n. So the first one is factorial 1, the second one is factorial 2, factorial 3, and it continues till factorial n. If you notice this, well, the only independent variable here is n. It is not m, because m we know to start from 1, and it continues step by step until it reaches n. So let's see how we can program this function 3. Well, we've already defined the function factorial in the last while we were making function 2, so we're just going to reuse it. So double function 3 integer n, right? There's only one independent variable here, which is n, so we need to pass that on. So because it's a running summation, for running sums you always initialize the answer to 0. For running products, as we would see in function 4, you would initialize answer to be 1. But right now, because this is a running summation and 0 is our additive identity, so we're going to just initialize answer to 0. So here we can say I starts from 1. We're going to use a for loop where I starts from 1 and it continues till it reaches n, and that's what we see here. I starts from 1 and every loop is incremented by 1 up until it reaches n, and the answer is really answer plus factorial I. So it's really a very simple function. Going back to the main function, now we can see 3 of these have been colored blue because we've considered how to write them. So the only function here is function number 4. And if you look at this function number 4, the principal component is r raised to the power l, and we've already discussed in function 1 that it's really a power function, and we can really put power r comma l here. So we just need to include cmath once at the beginning of the program. We don't really need to include it every time. And once we have included the cmath library, we can call out the power function as many times as we want. And what you see here is this summation. This is a symbol for product. So that means it's going to be power times power times power times power. This is a symbol for summation. So you have plus and plus and plus that continues to come after every element of the series, while here it's the product, and hence the times symbol appears here. So the first case is power r comma 1 because l changes from 1 to k. So in the first case is r comma 1, in the second case it's r comma 2, in the third case is r comma 3, and this continues until you reach r comma k. Notice here there are 2 independent variables. The first one is r and the second one is k. L we already know because L starts from 1 and ends at k. So if we want to see how to program this function, well, the first thing you should notice here is function number 4 has two independent variables, r and k. Once again, L is not independent, rather we know L completely because it starts from 1 and ends at k, and we will use this in the for loop. So we see here the function 4 has two arguments, one is integer r and the other is k. Because this is a running product, this time our double answer has been initialized to 1 because 1 is the multiplicative identity. Anything multiplied by 1 is the thing itself. So a times 1 is a. So that's why for running products we use 1 to start and initialize our variable. For running sums we start 0 because b, anything added with a 0 is the thing itself. A plus 0 is a itself. So for running sums, our initialization starts with 0. So now we see here the for loop, it actually starts with 1, so I is 1, and it continues to update one by one until it reaches k, and that's what we see here. I has been assigned to 1, I is less than k, and I is incremented. And lo and behold, the function itself is actually fairly simple because answer has been assigned as answer times power r comma I, where again we see this power r comma I coming up consistently and I continues to change. So now that we have really figured out how to make these functions independently, we can now combine them together to come up with this really complicated function. So the function has three, we can see here, 3 independent variables, so we put them here, integer k, n and r as arguments, and really the answer is just function 1 times function 2 times function 3 times function 4. Notice here that this is just one programming statement. I've included it into 2 lines only because the space here is less, but for the sake of correctness I've only put one dashed line, so each dashed line represents a programming statement. So now that you can see here, because of these functions, this very complicated function was really divided into small, easily manageable tasks and then combined together to form this very function. So let's try running this code in cpp.shell. So I'm going to go quickly to cpp.shell here and this is our program. Notice that it starts from our IO stream and then I've included the cmath function. And then there is this double factorial and then function 1, function 2, function 3, function 4, and lastly the double function, which is basically the product of all the 4 functions we've just defined. Because it's a function and we need the main function to run the program, I've just included a simple cout statement where I've just arbitrarily chosen k, n and r to be 3, 4, 5 just to see how it works. You can see the total code is just about 53 lines of code, which includes obviously the spaces and the brackets, curly brackets. So when I run this, you can see here the function 3, 4, 5 gives you 3300. So because of these functions, which we will be using extensively throughout the whole course, you can really divide larger, more complex tasks into smaller manageable tasks. And in fact this does help you a lot because these smaller manageable tasks are easier to debug. You can actually figure out the errors much simpler because each function is independent, and there are functions obviously which depend on other functions. Again, I would strongly recommend you try to write this code yourself and run it. Okay, up until next time, thank you very much. Bye bye.